Good morning, good afternoon, good evening, everyone. Thank you for joining us today. Welcome to this webinar, part of the ongoing series hosted by ISO Technical Committee 347, Data-Driven Agri-Food Systems, as part of our commitment to transparency, engagement, and inclusive participation in the standards development process. ISO TC 347 is a new and ambitious committee working to develop international standards that enable trustworthy, inclusive, and effective use of data across agri-food systems. My name is Andres Ferreira. I'm the chair of TC 347, and I'll be your moderator for today's session. Our webinar series is designed to explore key technical areas where standardization can support innovation, sustainability, and interoperability in agri-food systems. Today's topic is My Robot Saw a Bug: Automated Observations and Integrated Pest Management. It relates to the key driver of agricultural decision-making, observations such as those made scouting a field for pests. TC 347 has a large stake in finding ways to make observations and measurements data interoperable across the industry to enable the role as a pillar of principal decision making and to enable the use of technology to complement human activities in the field. Today, we will describe how observations and measurements are a key part of integrated pest management. We'll describe the role that standards have in enabling the scalable exchange of observations and measurements data. We'll introduce two use cases of technology-assisted observations and measurements in IPM. We'll share a simple proposal for related action within ISO TC 347, and we will show how you can actively participate in shaping upcoming international standards. The session's being recorded and will be made available after the webinar. Please feel free to post your questions in the Q&A box or in the chat. We'll address as many as we can during the Q&A segment at the end. We're very fortunate to be joined today by Dr. Zhang Haowen and Harrison Fuller, who will lead us through today's discussion. Zhang Haowen is an associate professor at the Institute of Plant Protection in the Chinese Academy of Agricultural Sciences. His primary research focuses on the monitoring and early warning of migratory pests. He specializes in monitoring and forecasting technologies, including insect radar, computer vision, and migratory trajectory prediction. He's published over 20 related research articles in international journals and holds 4 patents and multiple copyrights. He's contributed to Chinese standards development processes. His accomplishments have been recognized with honors, including the National Outstanding Innovative and Entrepreneurial Postdoctoral Fellow and the Outstanding Postdoctoral Fellow of the Chinese Academy of Agricultural Sciences. Harrison Fuller earned his Master of Science in Food Science from Washington State University in 2021, specializing in flavor chemistry at the Washington State University Wine Science Center. As lead spatial analyst for Syngenta's vegetable R&D IT, he bridges agricultural science and technology to advance precision farming solutions. Since 2021, Harrison has contributed to the ISO 7673 Parts 1 to 3, shaping international standards for agricultural data. His work includes Syngenta's open source biodiversity sensors, demonstrating his commitment to collaborative innovation. Harrison champions data standardization in agriculture, enabling farmers to adopt emerging technologies with confidence. Let's get started. Harrison, you have the floor.
All right. Thank you, Andres. So let's talk about robots, bugs, and automated observations and integrated pest management. To start, I want to start with some context of observations for IPM. This is where we see challenges intensifying globally. And what this means is things like climate change are expanding pest ranges. So we're seeing species show up in regions where they've never been seen before. But moreover, farmers, especially smallholding farmers, are often ill-equipped to deal with monitoring, identifying, or responding to these pest threats in a principled way. From the market or government or regulatory side, there's increasing pressure towards principled decision making and crop protection. And an example of this would be the EU farm to fork strategy, which targets a 50% reduction of crop protection or pesticides used by the year of 2030. So what do we mean when we say principled? Well, we mean that you monitor first, you establish whether some criterion for action has been met, you choose the least invasive effective control measure, and then you document why you did and what you did, all of which requires data, quite a bit of it, and this data needs to be interoperable. So in the context, the scale of pest management and the challenges demand automation, and automation demands interoperability, and interoperability demands standards. So how does integrated pest management, or what does integrated pest management actually entail? Here's the IPM business model, business capability model. And what IPM does is organized into three pillars, where we have prevention on the left-hand side. Prevention is the proactive capabilities before a pest problem occurs. This will include things like crop variety or selection, so choosing resistant or tolerant cultivars. This will also include things like crop rotation, where you break established pest cycles. And the second pillar, we have monitoring. Monitoring is the core analytical capabilities that inform decisions. Within monitoring, we identify the pest, or what is your threat. We evaluate severity, so how bad is our threat. We also establish spatial distributions, so where is our threat coming from? And then we can characterize the environment, so what conditions are driving this phenomenon. And the third pillar here, we have control. And control is the response capabilities ordered by intervention intensity. The interventions listed here could be cultural practices, mechanical practices, biological practices, or in last resort, chemical applications. This business capability model is in line with the architecture for crop care for integrated pest management, but today we're primarily going to be focusing on the monitoring pillar. Specifically, what happens when you automate monitoring with smart devices, the need to standardize the data that comes from smart devices. So let's consider monitoring as an everyday context. If you're a grower or growers around the world may be asking several questions. Questions like, are there armyworms in my field? Is the infestation bad enough to spray? Maybe you're asking questions about what's happening in neighboring farms. Any of these questions or answering these questions at scale using, say, a regional monitoring framework requires data exchange between multiple systems. Within these systems, you have components like a data collection application or a piece of hardware. Maybe you're using spatial interpretation tools that turn point observations into coverage maps. You may be using weather data from one or more vendors. And then at the end here, you'll be doing some analysis. So you'll be contextualizing pest observations against weather data, crop phenology, or other economic criteria. Each of these components listed are produced by different vendors, which contain different formats with different assumptions about what a pest observation looks like. And without standards, every integration of these vendors becomes a custom translation, and that gets expensive quite fast and does not scale. The following slide will hope to make that point visually. So on the left-hand side here, without standards, every device platform pair requires a custom-made integration. Now, it's hard to convey succinctly, but consider if you have 5 trap manufacturers, maybe 3 weather data providers, 4 farm management information system platforms, you're potentially creating 5 times 3 times 4 or 60 custom translation layers. On the right-hand side here, we have standards. Data producers speak the same language as the data consumer, and everything is ingested without custom translations. With a common standard, instead of 60 custom translations, we narrow it down to 12 implementations on one interface. With this, the burden of the data interoperability is shared between the whole value chain. And this is why we need to look towards other standards like 7673 series and specifically why we need to check that integrated pest management monitoring use cases are properly addressed. So what do standards promise in the context of integrated pest management? Well, standards promise to enable interoperability, and interoperability enables automation at scale. So what do we mean by scale? For example, a trap manufacturer in China or a trap manufacturer in Brazil can produce devices whose data can be used on the same observation model. Another example could be a national plant protection organization, which aggregates pest pressure data from thousands of heterogeneous devices into an early warning system. A third example here could be a farm management information system that consumes trap counts, weather data, or some actionable criteria, and then generates recommendations. All of these examples are assumed to not have custom per device integrations. So how do we get to this standardization point? We can use building blocks. Some of these building blocks will include standardized workflows, metadata management, encoding formats, controlled vocabularies. Vocabularies like code lists for pests, devices, or monitoring methods. Another building block here would be configuration management. So how do you describe what a device is and how it's set up, which is all complemented and addressed by ISO 7673 Part 2 and the work of Ad Hoc Group 7. The key insight here is that automation depends on interoperability, and you can't build new or novel automated early warning systems if you first must have to manually translate 15 different trap formats. So now let's look at the scope of TC347, data-driven agri-food systems. And I'm not expecting you to look at or read this whole block of text, but I do want to point out that IPM is explicitly listed within our scope. It says, integrated pest management and enabling traceability of food ingredients of agriculture and non-agricultural origin. So this is exactly what the strategic business plan identifies in TC347. And what we propose isn't a stretch of the goal, it's core to what the committee exists to do. Now, I do want to point out that the work that we're proposing would sit in Ad Hoc Group 4, Integrated Pest Management, or a new dedicated ad hoc group, which we'll discuss more at the end. So how does TC347 frame data-driven agriculture? It does so using 4 phases of a decision cycle. The first phase, informing your decision. This is where you're gathering observations, data, and context. In terms of IPM, this may look like monitoring or scouting. You collect pest observations, weather data, trap counts. In the second phase, you have making your decision. This is where you're evaluating criteria, selecting actions. In IPM or integrated pest management, you could be looking at things like economic injury, model outputs. And the third phase here, we have executing the decision. So carrying out some action. This could be spraying, releasing biocontrols, all in the form of work orders or application records. In the fourth phase here, we have evaluating your decision. So measuring outcomes, which feed back into the next cycle. In terms of IPM, this could be post-treatment observations or observing crop yield impacts. Within these 4 phases, it's important to understand that the decision cycle applies across the entire crop cycle. So from planning through post-harvest. Different processes of the crop cycle may emphasize different decision-making phases. So for example, here, if we look at planning and prevention processes, it may be heavily weighted towards informing or the making phase. In informing, we have field history or pest risk models. In the making phase, we have variety selection, rotation-based choices based on previous pest data. An example for crop care processes, which is where IPM monitoring lives, we'll have multiple iterations of this cycle. You monitor repeatedly throughout the growing season and reevaluate criteria at each time. A third and last example here would be post-harvest. And post-harvest, we're evaluating. This is where we determine if a season's IPM strategy was effective. The important point here is that monitoring data, the kind that we hope to standardize today, is feeding into every one of these processes. So historical pest records inform prevention, Real-time trap data drives in-season decisions, and post-season summaries guide next year's planning. So the following is TC 347's strategy, which is a pyramid with 4 levels. In layer 1, we have semantic resources. This is where we agree on what things mean. This will include things like registries of code lists, controlled vocabularies, object definitions. For IPM, this is where pest species codes or monitoring method codes and damage type vocabularies will live. In layer 2, we have master data and resources. This is where we agree on the resources involved. This will include things like data models for farms, field boundaries, parties, devices. For IPM, this is where smart traps need to be described as a device resource. So where it is, what it's configured for, what firmware it runs on. In layer 3, we have core documents. This is where we agree on things happening or how things happen. Within this, we have data models for plans, recommendations, work orders, work records. And this is most closely related with the series from 7673, parts 1 through 3, observations, field operations, and the core documents. In layer 4, we have inference. So this is where we agree how to use what we know. These are the tools for data-driven problem solving. These can be AI applications, load calculations, decision support systems, and such. So where does IPM monitoring work sit? Well, we hope that it sits primarily at layer 3. This is where we'll be checking the 7673, part 2 observation models cover pest monitoring use cases. But do you want to note here that we'll also be touching on layer 1 for vocabularies, layer 2 for device descriptions. And important to note here is that we'll be looking towards 7673 for its reusability as a framework. So we don't want to build anything new here. We just want to check that existing standards work for this domain. Now we'll peer a little bit into our first use case of IPM observations, the smart pheromone trap. These are typically low-cost devices deployed at scale for monitoring specific pest species. The components typically are a pheromone lure, which attracts target insects, typically adult males. You'll have some kind of observing module, which is an infrared counter or a camera. This will count or photograph trapped insects. You'll have some telemetry protocol, so you can think of cellular or low power wide area that sends data to a cloud platform. And then you have the cloud infrastructure itself for storage, processing, and visualization. All this together will enable some downstream use cases such as scientific pest control guidance or just generalized pest monitoring. So what is the information that we get from these traps? Well, essentially, you get 2 main outputs. You have a classification component. This is where you identify species of a trapped insect. In manual traps, a human expert will identify these species. In a smart trap, maybe a machine learning model trained on human annotated images does the identification for you. The second component here is that you get some kind of count over time. This is the monitoring and core to our business capabilities model. So how many individuals per time period do we observe? This is what the chart is showing on the right, where the y-axis is count and the x-axis is time. And what you're looking for are trends. Is the population increasing? Has it evolved into an actionable criterion? This becomes a critical standardization point for these 2 outputs, both classification and count, and they must be consistently represented across vendors. Now, let's say you have a network of traps, say dozens or hundreds across a particular region. What you end up being able to do is build spatial pest pressure maps. And this slide attempts to show exactly that. You have individual trap observations or points that are interpolated to a continuous surface showing pest pressure levels. This could be like low, moderate, or high. What this does is establish your spatial distribution, and this is a distribution capability from our business capability model. Again, this is where standardization or the value of standardization really shows. Now, and then if every trap follows the same observation model with the same spatial scope, your interpolation of pest pressure becomes a little bit straightforward or more straightforward. Now, on the flip side, if you have different trap vendors that use different coordinate systems or different count metrics or different severity categories, every integration requires some custom mapping. So now let's look at how one vendor actually organizes their trap data. And the following is a mind map of a real vendor's data hierarchy. And around the circle, we can begin with context. This is the context of the organizational metadata that precedes the observation itself. This can include things like credentials, organizational information, device identity, pest target, crop time zone, sensor configurations. Next, we can move on to observation and device data or the actual payload. This can include things like event type, status, count, spatial extent, classification, images, raw or processed. And the point of this slide is that real vendor data has a rich hierarchical structure. And the question isn't what data exists, because we know vendors are already collecting everything they need. But the question now becomes, can ISO 7673 represent the hierarchy faithfully, or can we map every element of this slide into a concept in the standard? I will now pass it over to Dr. Zhang to talk a little bit more about insect radar.
Okay, it's my turn. Thank you, Harrison. Hi everyone, I'm Zhang Haowen. I'm very glad to share with you the use case to insect radar. What is insect radar? Insect radar is a radar system specifically designed to detect migratory insects. It serves as an important and the next generation insect monitoring tools under all weather conditions, comparing traditional tools such as high altitude satellites. But analyze the radar echoes, parameters such as flying height, flying speed, flying direction, and quantity, wind speed frequency, body length, body mass, and body wise, and such as these biological characters parameters can be calculated by insect radar in real time. Maybe we will have a chance to share a technical report on recent insect radar sometimes in the future. As shown in the figure on the right, based on the operation models, commonly there are two kinds of insect radar, including scanning insect radar and vertical looking radar. The scanning radar designed the antenna of the scan radar can be rotated 316 degrees, both horizontally and in elevation, making it suitable for wide range observation. And the vertical looking radar, on the other hand, is designed for small scale and high resolution observation and obtain more detailed parameters of detected targets. Okay, next slide. Thank you. And what insect radar tell us? As shown in the figure, we present example of image collected by a real vertical looking radar for insect targets. Each bright spot represents a target detected by the radar, and the x-axis is time dimension, and the y-axis is height. And the color coding displays the radar echo intensity of each target. Typically, we first use object detection model to extract individual targets, then calculate various parameters with dedicated algorithms. Based on these parameters, machine learning models are further applied to classify the targets. For example, distinguishing insects from birds, as well as different insect species. This is example. Yeah, okay. Next one, next. Thank you. Next one, okay. And this example of data collected by insect radar. Record time represents the actual a time when the target occurs, while the insert time refer to the time when the process results are recorded, and the other parameters contain the biological parameters such as body length, body mass, body width, and wind beat frequency, and flying parameters such as flying height, flying the horizontal flying speed, and the vertical flying speed. I think most current vertical looking radar system are capable of collecting this type of data. But of course, the data collected by scanning radars may differ from this example, but I believe this can serve as a good reference for other radar systems. So in the future, we can adopt ISO standards to enable different radars to speak the same language, which can greatly improve the joint analysis of data from multiple radar systems. Okay, thank you. Next one. Yes, as Harrison showed us, here is monitoring radar data from a vendor perspective, and it's focused on the constructive, practical, and standardized data structures for engineer deployment, interconnection, and industry application. It usually includes the four core components. For example, the credentials, organization, device, and the data collected by the inside radar. And I think this struck the design issue, the data scalability and the analyst for the actual operation and pest monitoring service. And all this data, all these things are supported by the ISO 7673. Okay, thank you. That's all.
Thank you. So why do we need to address IPM observations and measurements in TC 347? What the diagram below is showing illustrates the following. So you have data that moves from the edge or a field device. That data is transmitted via various protocols into some cloud infrastructure where it's aggregated and analyzed for a downstream data consumer. Now, without standards at each of these interfaces, this pipeline becomes fragile or vendor locked. So why can't the market solve this problem on its own? And there's essentially three reasons. So reason number one, we have diversity of equipment. If we look at these images on the right, we have things like pheromone traps, light traps, insect radars, drones, weather stations, handheld scouting devices. Each of these manufacturers have their own data format, metadata conventions, and transmission protocols. Ironically, no single vendor has enough market power to impose a de facto standard. The second reason here is that we have data format and transmission heterogeneity. So without agreed upon standards, every integration between a monitoring device and a decision support platform becomes a custom project. This limits what data integration across systems and regions can really do. And you actually find yourself in a situation where you're unable to compare trap counts from two different vendors or manufacturers without some kind of manual mapping. The third reason we have is data integration challenges. Again, there's no agreed upon methods for how you spatially align or how you align spatially temporal or multi-source monitoring data. How do you combine daily trap counts with hourly weather station data or weekly drone imagery and make a coherent pest risk assessment? This will require a lot of common formats, but also common semantics. So there needs to be agreed meaning on what it means as a pest observation, what is a phenomenon time, what does severity represent. This will be the last part of our talk. So we've seen how environment or government influences complicate IPM. We've seen how we envision standards to work with integrated pest management. And we've also seen how the marketplace is increasing the scaling complexity of integrated pest management. But we do have targets for applying existing standards and reuse it so we're not starting from scratch. There are several standards that already exist and are directly relevant to integrated pest management. For example, we have ISO 7673 Part 2, Observations and Measurement. This will be a primary target for gap checking. It implements ISO 19156 Observations Model for Agriculture. It defines how to represent observations, their temporal and spatial scope, their observed properties, their features of interest, procedures, and results. As we saw in earlier slides, it already covers much of what trap and radar vendors need. A second example here is ISO 5231. This will provide communication framework, including MQTT-based messaging for farm information management systems. This is really relevant to the device-to-cloud transmission layer. A third example here would be ISO 30161, IoT data exchange. These will include general requirements for architecture of IoT services and data exchange. This will provide broader frameworks for our pest monitoring devices to be compatible with. In this prior work approach, what we're aiming to do is, again, gap check existing standards rather than creating something new. This will be a more efficient use of TC 347's time, as well as checking consistency across the work being done. What we hope to learn from IPM gap checking will be applicable to other observation domains. So think about soil health, water quality, or even animal welfare. So here's our call to action. What we're proposing is creating a new ad hoc group within TC 347. We'll name this Observations and Measurements in Integrated Pest Management. What this group will do is first collect a set of use cases for observations and measurements in integrated pest management. But this group will also gap check the observations model of 7673 for integrated pest management monitoring use cases, specifically automated tools like smart traps or insect radars. In this gap checking process, the expectation or the critical point here is that what we learn will be applicable for other groups that are working with 7673 Part 2 observations model. So this isn't just an IPM exercise, it's a test case for the reusability of the observations framework, where we will confirm what works, we'll identify what's missing, and we'll produce implementation guidance that makes adoption straightforward. This group will also draft technical reports. So as Dr. Zhang mentioned about insect radars and integrated pest management technologies, we'll be surveying device landscape, identifying data requirements, and standardization opportunities. The group will also propose or produce new work item proposals or other deliverables, so potentially extending ISO 7673 Part 2 for specific observation types, controlled vocabularies for pest species, monitoring methods, and again, implementation guidance. This group will also coordinate with existing groups, so Working Group 1, Ad Hoc Group 7, 8, 9, and 10 to ensure broader alignment with the TC 347 architecture. Now I propose a question to you or the group is why not just do this in Ad Hoc Group 4? Well, essentially it's because the skills are different. Ad Hoc Group 4 focuses more on IPM processes. This will include things like the business capability model, the decision cycle, the workflow. But the observations model requires work around, or it requires expertise in ISO 763 Part 2, data encoding, IoT transmission protocols, device data architectures. And essentially you have different people with different cadences. For our work, some of our target participants will include IoT device manufacturers, so trap makers, radar system providers. Participants should also be national plant protection organizations or FMIS vendors with IPM functionality. We also want to target academic researchers, researchers in entomology or agricultural informatics, as well as liaison organizations like OGC or even Ag Gateway. And with that, I pass it back over to Andres.
Thank you, Harrison. So for our final point about how you can participate, in TC 347, most of the work happens online. We have a couple of plenary meetings every year where the whole TC gets together, one of which is virtual, happens in October, and the other one, which is in person, which is coming up next week for us in Cologne in Germany. And those are great because everybody comes together and we sort of reconnect on what we're doing, what the overall strategy is, and where each part, like the one that we're discussing here, fits. But most of the work really happens within our subgroups. So working groups, ad hoc groups, advisory groups. Those meet more often, but they set their own schedule. And within those groups, there's two ways of contributing. One is through your national standards body. If your country is a member of TC 347, that membership is expressed through a national mirror committee that is organized by your national standards body, sometimes by delegating it in another organization, like, say, ANSI in the US delegates the National Merit Committee for TC 347 to the American Society of Agricultural and Biological Engineers. In Canada, the Standards Council of Canada delegates managing the National Merit Committee for TC 347 in CSA and so forth. So that's the best way to participate because you can participate directly in the work itself in the groups, and then you can help your country vote on the different ballots that emerge. Another way of participating is through a liaison organization. TC 347 currently has relationships with 10 such organizations, a few of which have been mentioned today, like Gateway, OGC, and so forth. These organizations establish liaisons with us, and it allows them to allocate representatives to our work, including to the working groups. They don't get to vote, but they do get to participate in the working groups and roll up their sleeves and help. For any questions you might have, please contact us. We have an email address, or you can email me. We have a LinkedIn page. We have a main ISO page, and that URL you see there. We'll share these URLs in a moment. So with that, I think it's time for us to ask some questions. Okay, so I think I'll start with one. And please, folks, either put your questions in the Q&A or in the chat. So the first question I have is for Haowen. It has to do with the insect radar, right? That's like really interesting to me, and it's not something that I have prior experience with. I know traps well, but not radar. So how is insect radar used operationally? What kinds of problems does it solve?
Okay. Typically, the radars are usually deployed along the key migratory pathways and operate the 24 hours for continuous monitoring, and then it can to monitoring all kinds of flying insects, because as we know, most of the pest insects are fly in the night, but some of them fly in the daytime. And with the insect radar, we can monitoring the population dynamics of the airborne flying insects in real time. So it can provide us data support for the pest control and also the protection of the nature enemies. Yes, because we can classify the different species of the targets. So I think is totally is solved key problems, including the early warning of the large scale pest outbreaks, and also can classification of the species of the uh, uh, objects that's detected by the radar. Yes, and it also can support the press support the pest control, reduce the pesticides, and yes, and protect the natural enemies. I think as a ecological level. Yes.
What's the range? What's the range of an insect radar? What kind of
Uh,
radius can it monitor?
to, always 2,000 meters because the
2,000 meters. Okay.
2,000 meters because the insect doesn't fly that high or always
Okay.
fly under the 2,000 meters.
So, sort of farm scale, if you will, or multiple, like at a community level, if you will. Okay, that's very interesting. That's certainly further than what a trap can represent. I can imagine training such a radar must be to distinguish different species must be very tricky. Um, a question for Harrison. Um, I noticed you singled out configuration management as an enabler of interoperability. What do you mean by configuration management, and why is it important?
Yeah, so with configuration management, I am talking about how you as a user may have to set up the device itself. More often than not, these devices are dumb in a lack of better terms, in that it doesn't recognize if you put one cord in port one or one cord in port two. So downstream, if things fail, configuration management will allow you to do some triage or understand what went wrong, why it went wrong, and perform some corrective action. Uh, yeah.
Okay. And I guess managing where you put the device over time and making sure that you um, really know where it is and are guiding decisions based on where your device really is an important part of this too, right?
Mhm.
Um, okay, then we have Delphine, one of our YPP participants from our Young Professionals program. She picked up on the tongue-in-cheek robot designation here, although we haven't talked about things that move, and I know that the industry is avidly exploring scouting robots right now. But her question, I think for both of you, let's start with their second question first, which is how accurate are these traps or the radar compared to a human expert? This is in terms of identification. This is quite different for traps and radar, right? Um, do you have a sense of accuracy?
Yeah, in terms of traps, accuracy in terms of IDing is quite good. I've seen IDing accuracy as high as or over 90%. When you start looking into the count numbers, the accuracy may go down a little bit as some artifacts are collected on like a sticky trap, for example, that the machine learning model can't quite differentiate. But usually have some human in the loop that will correct for obscure counts.
Mhm. And Owen, how about radar?
Yes, radar. I think when we want to count the number of the insects, I think the accuracies are high because it's easy for human to detect the and actually all the AI models trained by people's knowledge. Yeah, so I think this is very simple tasks. But if you want to uh, classify the species, I think it's very challenging work. for radars, because when you observe a lot of insects, but you can't know the ground truth. Actually, we use the high altitude satellite to capture some samples of the moths or some flying insects, and to record the flying peak, and it is kind of an event, flying event. So we record this data and to add our model to train to add the ground truth. I think the accuracy for to classification of the species, as it depends on the how many data we have and how many events we observe. Yes.
And sometimes um, your aspiration to accuracy will be limited by the technology, right? So um, many species of bumblebees might appear the same to radar, for example, just to give an example, because they have similar size, they fly in a similar way with similarly sized wings, and you can typically only tell them apart visually at close range, which is something that radar can't do. So in that case, you might be limited to only identifying at the genus level, right? Like saying this is a bombus, but you can't know which one. Um, and this leads me to another question, and we'll come back to Delphine's second question before. Um, Harrison, you've worked on this kind of technology before of using sensors to identify insects, but related to biodiversity, right? Where you've been involved with testing different kinds of sensors and was sort of engineering a device to make observations. And you've also worked with actual sticky traps using machine learning models and so forth to identify insects via imagery. How are the two applications, the biodiversity and the IPM one, different or similar? Um, can you give us a little bit of
Yeah,
um,
so with, I mean, if we go back to the data-driven decision-making process, you essentially have, well, I mean, they all follow very similar phases and processes, other than the fact that for IPM, your actions may be control to kill, but in biodiversity, your actions are entirely different. And in terms of uh, what biodiversity allows you to do is kind of expand on these longitudinals or kind of long time frame studies that allow you to realize how your integrated pest management actually may be infecting your overall biodiversity for your particular field or region. So there's a lot of interactions there that become quite interesting, but it is often quite difficult to monitor biodiversity because you have to be very specific about what kind of biodiversity you're looking at, right? So you mentioned bees earlier. Are you looking at bee populations? Are you looking at ladybugs? You know, how you target these things becomes rather important.
Thank you. Um, then let me ask. Got two questions or one question and a comment. Um, for both of you, starting with Haowen, um, Delphine asked, "What's the most unexpected thing that you've detected in the field, or what's the most unexpected thing you've found out from engaging with this technology?"
Um, for me, for the insect radar, the most exciting thing is I think finding the migration peak of the insect pest. Yeah,
Okay, so being able to see how the migration
yeah,
looks in the radar, like saying the amount of individuals goes up over time, then peaks, then goes down again.
yeah.
Okay,
Yes.
that's interesting. And just the visualization that you do of time as the x-axis in your picture, that's so intriguing. Like you really set up to see that migration peak as you mention it. Um, it makes me think of the Matrix or something like that. Um, and how about you, Harrison? What's the strangest thing you've seen with the work that you've done in that space?
Oh, I wouldn't say strange, but it's nice to see uh, uh, contributors leave notes for you in your sticky traps. Words of encouragement. But it's also fun to just to uh, it's to Howen's point. It's interesting to see the peaks. So how quickly things can develop over the period of say 1 to 3 days in terms of a pest monitoring situation, and they can change quite dramatically.
Excellent. Thank you. I think it's just so interesting to be able to remotely look at what's on a trap and be able to see how the count differentially increases over several days and how that rate increases. And then you're like, okay, got to take action. It's a very, very interesting technology. Then Baoqian Liu says we're citing what you mentioned about currently proposing a new work item titled Data-Driven Integrated Pest Management. Says given that both initiatives emphasize data-driven IPM, would it be possible to consider a cross-working group integration mechanism? Okay, so I think the conversation here is about this versus the idea of having an ad hoc group for, right? And so given that both initiatives emphasize data-driven IPM, would it be possible to consider a cross-working group? Yeah, for example, one group could focus on the data structure and interoperability aspects, while another addresses the process framework and implementation guidelines. Well, yeah, that's exactly the plan, right? In a way, very similar to how ad hoc group 10 exists from ad hoc group 8. Ad hoc group 8 was looking at operational data, and then the idea of working with field boundaries started coming up as an important thing. And so those leaders said, no, please spin this off because the people are going to be different. But then we agreed quickly on the relationship, which is that those documents, those core documents of the circle that Harrison showed earlier, we're just going to reference a field boundary using a unique identifier. And so then we were able to quickly set the stage for interoperability and not getting in the way of each other. But the ad hoc group leaders talk to one another all the time. And as chair, it's part of my job to architect situations where they interact and we test our hypotheses about interoperability, right? And so this is no different in that here there's an elegant mechanism for treating observations and measurements in a harmonized but somewhat independent way from the domain of integrated pest management or all the other domains. That's why Harrison made the point that we were looking to derive insights from here for other projects as well. There's very similar observations and measurements in different parts of TC 347. The new ad hoc group 11 on smart beekeeping, ad hoc group 12 on smart irrigation, ad hoc group, what would likely be ad hoc group 14 about externalities and sustainability using animal byproducts as an example. Clearly, there's a lot of observations and measurements to do there too. So I think we'll be getting into the habit of treating observations, constantly challenging our model to see if we can keep using it throughout, or if we need to make tweaks to generalize it even more, while at the same time making sure that that it keeps working for a particular domain like IPM. So yes, I think we're good. Last question: how to detect non-flying pests? Can radar detect ground pests? Um, I don't think so, Haowen, right? I think that Harrison has done work on that front, which was somewhat frustrating with other sensors. But Haowen, is there any work done with radar on the ground?
Um, non I'm not sure. Non-flying pest. What is this kind of? Is it like a larvae or just kinds of moose just flying over
I
the ground?
think like larvae, caterpillars and um,
Uh, it's
things like that.
I don't think the radar can detect the larvae in the ground. It
Mhm.
can only detect the flying insects. Yeah.
Yeah. Um, Harrison, do you have any insights about that?
Well, from a camera perspective, we've seen cameras literally pointed at the ground, trying to use lures as well to attract things like beetles or larvae, like you mentioned, or worms. So, not a great success on that front, but there has been some attempts there.
Yeah, I've also seen attempts on um, soil soil organisms, right? An interesting indicator of soil health is the ratio of the count of mites in a certain amount of soil to the count of collembola, the springtails in there. Mites being more um, fragile or more sensitive to environmental conditions um, than collembola. The ratio of how many of each you see can give you a sense of the state of that soil. But that requires taking samples of the soil and running them through a piece of equipment, right, where you sort of lure them to the bottom where they can be counted. Uh, then we have from Rafael, another member of the YPP, says, congratulations on the presentations. It's really interesting to learn more about the subject. Excellent materials, super organized. Thinking about farmers, how long will it take for technologies like this to be implemented in large scale farming? Rafael, that's why we have a TC347 that you're starting to participate in. Those sticky traps exist, right? And the problem is that it's hard to make them interoperate at large scale. That is a real problem. And that's why we're trying to do this work. Likewise, there's multiple manufacturers of insect radar, right? It's a very promising technology. We need to enable their wider use. Okay, so folks, we're out of time. Thank you so very much. Um, the We will email all of you some information like these slides. When we put this webinar online, we'll also email you that. And someone asked for the email of the presenters. We'll include that in the material we email you. Okay, so thank you very much. Have a great rest of your day. And we will see you again at our next webinar. Thank you.